They weren't supposed to find it. Not this soon. Not in the ancient light of a universe barely formed. And yet, there it was, J1342 plus 0928, a black hole so massive, so luminous, so impossibly old that its very existence challenged the foundations of modern cosmology. It began in silence. A faint, unfamiliar glow recorded by a wide-field infrared sky survey. No one paid it much attention at first, just another red speck among countless others. But then the data came in. Spectral analysis. Redshift measurements. A number that froze the air in the room. 7.54. That meant this object, this black hole, was emitting light just 690 million years after the Big Bang. In cosmic terms, that's a heartbeat after the universe began. A time when stars were just forming, galaxies barely taking shape. According to prevailing theories, there shouldn't have been enough time for anything that massive to exist, not yet. And yet this black hole was already over 800 million times the mass of our sun. Scientists stared at the data. Some thought it had to be wrong. A misreading. A glitch in the calibration. But after a dozen independent verifications, the numbers held. The object was real. It was ancient. And it was impossibly huge. In the standard model of cosmic evolution, black holes grow slowly. They begin as remnants of massive stars, collapsing under their own gravity, forming compact cores that consume gas, dust, and even stars to bulk up over billions of years. For a black hole to reach nearly 1 billion solar masses, it should have required at least a few billion years of steady growth. Yet this one was already there, at the very dawn of cosmic time. So how? Some suggested that it was born from a supermassive star, perhaps hundreds of thousands of times the mass of our sun, that collapsed directly into a black hole, skipping the usual stellar life cycle. Others proposed more exotic origins. Primordial black holes formed just moments after the Big Bang, seeded not by stars but by fluctuations in the very fabric of space-time. But all of these ideas carry problems. If such massive stars had existed, why had we never seen signs of them elsewhere? If primordial black holes were common, why hadn't we detected more of them? Still, the object couldn't be denied. J1342 plus 0928 sat there, a brilliant beacon at the edge of the observable universe, emitting powerful radiation as it gorged on surrounding matter in a process known as accretion. It wasn't hiding. It was shining. Its light had traveled for over 13 billion years to reach us. It began its journey when the universe was less than 5% of its current age, before Earth, before the Sun, before the Milky Way. And in that light was encoded a challenge: find an explanation, or admit we don't understand black holes as well as we thought. The discovery sent ripples through the astrophysics community. Theoretical models were rechecked. Cosmological simulations were rewritten. The timelines for black hole growth were scrutinized and stretched. Could accretion happen faster under extreme early universe conditions? Could there have been an abundance of cold gas ready to feed this newborn giant? Some researchers proposed super-Eddington accretion, a scenario where the black hole consumes matter at rates higher than once thought possible. Others looked at dark matter halos, structures of invisible mass that may have funneled gas into the black hole's grasp, accelerating its growth. But none of these explanations felt complete. They were patches, not answers. Because behind every theory was the same uneasy truth. We were seeing something that should not exist. Something that violated the chronological logic of astrophysics. Something that forced us to question whether our models of cosmic infancy were missing a crucial piece. As telescopes improved, more ancient black holes like J1342 plus 0928 began to appear. Not many, but enough to suggest that this wasn't a one-off anomaly. It was a pattern. And patterns, in science, demand explanations. That's when the whispers began. Quiet, hesitant suggestions in conference hallways and academic journals. Maybe our assumptions about time were off. Maybe cosmic expansion wasn't as linear as we thought. Maybe something happened in the early universe that allowed for shortcuts, mechanisms that allowed mass and structure to emerge faster than our equations predict. The mystery deepened. The ancient black hole became more than a curiosity. It became a symbol, a cosmic paradox hanging in the darkness, reminding us how little we truly know about the first billion years of existence. And yet, it also became a beacon, a focal point for inquiry, debate, and imagination. Because if such a thing could exist, what else might be out there? What other relics from the cosmic dawn are waiting to be discovered? In pursuit of answers, scientists began to look not just forward, but backward, to the very beginning, to the instant of creation itself. because only by understanding the conditions of the universe's birth could they hope to explain the impossible presence of something that, by all rights, should have taken eons to grow. It was time to go back, to the earliest flickers of light, to the primordial fog, to the quantum tremors of existence. Somewhere in that chaos, the seeds of this anomaly had been sown, and that is where the next part of the story begins. In the immediate aftermath of the Big Bang, the universe was dark, not figuratively, literally. For nearly 400,000 years, it was an opaque soup of searing hot plasma. Photons couldn't travel far without scattering off free electrons. The cosmos was, in every sense, a fog. Then came recombination. As temperatures dropped, electrons and protons combined to form neutral hydrogen atoms. This decoupling of matter and radiation allowed the first light to move freely through space. We see this ancient light today as the cosmic microwave background, faint, stretched, whispering the temperature and density ripples from an infant universe. But even after that moment of transparency, the cosmos remained dark for a long time. The first stars hadn't formed yet. There were no galaxies, no planets, no black holes, at least none we can verify. This period is called the Cosmic Dark Ages. It's within this black canvas that the puzzle of J1342 plus 0928 begins to form. Somewhere between 100 and 200 million years after the Big Bang, the first stars ignited. These weren't stars like our sun. They were huge, hot, and short-lived, likely hundreds of times more massive, formed from pristine hydrogen and helium. Astronomers call them population 3 stars, and none have been directly observed. They are theoretical shadows, inferred from the chemical fingerprints left in second-generation stars. These titans burn bright and fast. Within just a few million years, they ended their lives in cataclysmic supernovae, dispersing the first heavy elements, carbon, oxygen, silicon, into the interstellar medium. More importantly, their deaths may have birthed the first black holes. If such stellar remnants were massive enough, on the order of tens to hundreds of solar masses, they would have collapsed into black holes. These seed black holes then had 2 paths to grow, accrete matter or merge with one another. But that's where the math breaks down again. The problem isn't that black holes grow. It's how fast they must grow to reach the size we see in J1342 plus 0928 in just 690 million years. If they grow at a constant, theoretically maximum rate, the Eddington limit, it still takes close to 1 billion years to reach 1 billion solar masses. So how do we reconcile this? Some theorists began to suspect the early universe was more chaotic than we imagined. Dense regions, rich in gas and free from the metallicity of later epochs, may have allowed for supermassive stars to form directly. Stars so large that they bypassed the typical life cycle and collapsed instantly into black holes weighing 10,000 or even 100,000 solar masses. These direct collapse black holes are hypothetical, but they could dramatically shorten the timeline required to explain objects like J1342 plus 0928. Instead of starting small and growing slowly, these black holes would start big and grow faster. To find supporting evidence, scientists turned to simulations, gigantic computer models that recreate the physics of gas dynamics, dark matter halos, star formation, and gravity across millions of virtual years. And in some of those simulations, rare pockets of the early universe emerged where temperatures and pressures aligned perfectly, allowing for runaway collapse. It wasn't common, but it was possible. Then came a different idea. Perhaps we were looking at the wrong scale. Maybe the problem wasn't about speed, but scale. If primordial black holes were seeded not by stars but by density fluctuations in the moments after the Big Bang, then their origin predates galaxies, stars, and light itself. This idea, that black holes could form from regions of extreme density shortly after inflation, is both exciting and controversial. It reimagines black holes not as endpoints of stellar death, but as fundamental constituents of the early cosmos. Some versions of this theory even suggest that dark matter, the mysterious substance that comprises 85% of the universe's matter content, could be made of ancient, non-luminous black holes. Still, no definitive observational evidence supports this theory yet, but it has one enormous advantage. It would neatly explain the existence of massive black holes at times when stars barely existed. In 2021, a paper published in Nature Astronomy highlighted yet another wrinkle. Using the Atacama Large Millimeter/Submillimeter Array, ALMA, researchers observed the region surrounding J1342 plus 0928 and found an unexpectedly mature galaxy, dust-rich. Star forming. Complex. In a time when most galaxies were still chaotic clumps, this one seemed ahead of its time. This hinted at a possible coevolution, that black holes and galaxies may have grown together, feeding one another, shaping each other's destinies from the very beginning. The galaxy fed the black hole with gas. The black hole, in turn, generated winds and radiation that regulated star formation. But that deepened the paradox even more. Now, it wasn't just the black hole that was too old, it was the entire ecosystem around it. How could such structure form so soon after the Big Bang? Was the early universe fundamentally different? Were we underestimating the efficiency of cosmic assembly? Or were we missing something bigger, something deeper in the fabric of time itself? Some cosmologists have floated the idea that cosmic time may not be as smooth as we imagine. What if, in the intense conditions of the early universe, time itself flowed differently? That certain epochs experienced brief bursts of accelerated structure formation? It's speculative, but the presence of these ancient giants continues to press against the boundaries of theory. Like time travelers, they sit in places they shouldn't, carrying mass they shouldn't yet possess, radiating clues we haven't yet learned how to interpret. And so, the deeper astronomers peer into the early universe, the more complicated the picture becomes. Instead of finding the simple, pristine beginnings predicted by models, they find complexity, contradiction, and surprise, which, in a way, is the most honest outcome science can offer. The early universe wasn't a clean lab experiment. It was chaos. It was creation. And in that swirling cauldron of matter and energy, strange things were born. Black holes that had no business existing, galaxies that formed too quickly, structures that shouldn't have stood. But they did, because the universe doesn't need permission to be weird. It just is. And as we stare deeper into the ancient dark, we realize, the more we learn, the more we have to unlearn. The story of this ancient black hole didn't end with its discovery. In many ways, that was only the beginning. As scientists raced to understand how something so massive could have formed so early, a new challenge emerged. Could this black hole be unique, or was it part of a larger population we had overlooked? To find out, astronomers scoured the sky for similar objects. They pushed deeper into the cosmic dawn, using telescopes capable of peering across more than 13 billion light-years. Each discovery added new weight to the mystery. These weren't flukes. They were part of a pattern. Take, for instance, the quasar ULAS J1120+0641, discovered in 2011. It existed just 750 million years after the Big Bang and contained a black hole with 2 billion times the mass of the Sun. Then came J0313, 1806, clocking in at just 670 million years after the Big Bang, with a black hole of 1.6 billion solar masses. These weren't edge cases. They were evidence of a systematic gap in our understanding. The data began to suggest something profound. The formation of massive black holes in the early universe may not be rare at all. Instead, it could be a standard outcome of conditions we still don't fully comprehend. Some researchers began to wonder whether our current models of galaxy formation were missing critical components. If black holes of this size and age were common, then the processes that built them had to be both efficient and widespread. That meant re-evaluating our theories of how matter cooled, collapsed, and coalesced into structures. One hypothesis was that these early galaxies existed in particularly massive halos of dark matter. These invisible structures, composed of unknown material, act as the scaffolding of the universe, guiding the formation of galaxies and clusters. If a region of space had an unusually dense dark matter halo, it could compress gas more quickly, triggering rapid star formation and black hole growth. But that raised another question. Why were these halos forming so quickly? The early universe, while dense and hot, was also governed by expansion. Matter should have taken time to gather. The presence of well-formed halos hinted at deeper forces, perhaps primordial density fluctuations more extreme than expected, or early quantum effects shaping large-scale structure. Meanwhile, other teams looked inward, literally, at the physics of accretion. The Eddington limit, often treated as a hard ceiling, isn't absolute. Under the right conditions, black holes could temporarily exceed this threshold. If the inflowing gas was dense enough, if radiation could escape along polar jets or irregular paths, then growth could be faster than models predicted. Super Eddington accretion is no longer just a theoretical possibility. Observations of black holes in the local universe have shown short bursts of feeding that defy the classical limits. Could such behavior be the norm in the early cosmos? Perhaps, but even with accelerated growth, the numbers didn't always add up. So some scientists turned to entirely new frameworks. One of the most radical among them involved modifying our concept of time itself. According to some theories in quantum cosmology, time may not be a smooth, uniform backdrop against which events unfold. Instead, it could be emergent, an illusion arising from entanglement and interaction. If true, then the age of the universe in conventional terms might not reflect the true complexity of its evolution. In such models, certain regions of the cosmos could evolve faster than others, not in terms of motion, but in information density. Structures could form earlier than expected not because time flowed differently, but because the rules that govern change operated under different initial conditions. This line of thinking is deeply controversial and profoundly difficult to test, but it speaks to a growing trend in theoretical physics. The realization that some of our deepest assumptions, like time and causality, might themselves be emergent features of a more fundamental framework. Meanwhile, observational astronomy continued its steady advance. With the launch of the James Webb Space Telescope, JWST, humanity gained a tool designed specifically to probe the cosmic dawn. Its infrared eyes peer into epochs previously veiled in darkness, revealing galaxies and quasars that formed just a few 100 million years after the Big Bang. Within its first year of operation, JWST delivered surprises. Galaxies with more mass, more structure, and more maturity than expected appeared in its data. The instruments detected potential black hole hosts with masses and properties at odds with simulations. Once again, the universe was faster, more efficient, more audacious than we had dared to model. Among the data, more ancient black holes emerged, some in dwarf galaxies, some in unexpectedly compact regions, all challenging the timeline. The notion that the early universe was slow to form stars and structures was crumbling. Instead, we were beginning to see a cosmos that hit the ground running. This new picture suggested that the epoch of reionization, the time when starlight relit the universe and burned away the cosmic fog, may have been driven not just by stars, but also by black holes. Their energetic outflows, jets, and radiation could have played a major role in transforming the intergalactic medium. If true, that meant black holes were not passive byproducts of galactic evolution. They were active agents, shaping, heating, and influencing their surroundings from the earliest times. One particularly elegant model proposed a feedback loop. Early black holes grew quickly, generated powerful radiation, and suppressed further star formation in their vicinity. But that same radiation could trigger collapse in nearby gas clouds, seeding new stars and black holes elsewhere. A kind of cosmic relay, with black holes as both sprinters and baton passers in the race of structure formation. All of this brought the field to an inflection point. No longer could black holes be treated as exotic endpoints or anomalies. They had to be integrated into the very fabric of cosmic history, early, active, and central. That required new simulations, new theories, and perhaps most importantly, new questions. Because when something as fundamental as a black hole defies your expectations, it forces you to reconsider not just the object, but the entire context in which it exists. The ancient black holes discovered in the early universe are not just strange outliers. They are guideposts, markers pointing toward the limits of our models. And as we follow them deeper into the past, we're beginning to realize that the story of the cosmos is far messier, faster, and more intricate than we imagined. We once thought the universe began in silence, then slowly built its complexity. Now we know better. The early universe was loud, with radiation, with gravity, with collisions and collapse. It was a crucible, not a cradle. And the black holes born in that chaos are not paradoxes. They're the truth. The deeper scientists explored these ancient anomalies, the more profound the implications became. It was no longer simply a matter of how these black holes formed. It was about what their very existence said about the nature of reality, the fabric of the cosmos, and the timeline we thought we understood. One of the most pressing questions was this: if these black holes formed so early, What were the seeds that started them? In modern galaxies, supermassive black holes seem to grow from stellar remnants or direct collapse mechanisms. But in the early universe, there might not have been enough time for even the most massive stars to live and die before forming a black hole of that scale. That forced scientists to reconsider what seed meant. Enter the concept of direct collapse black holes. Unlike stellar black holes that are formed from dying stars, direct collapse black holes bypass the stellar phase altogether. Imagine a massive cloud of pristine hydrogen and helium, untouched by previous generations of stars, collapsing under its own gravity, not into stars, but directly into a black hole. These would be enormous from the start, hundreds of thousands of solar masses or more. If this happened early and often enough, it could explain the presence of ancient black holes with billion solar mass scales. But that theory too has problems. For such a collapse to occur, the cloud must avoid fragmentation. Normally, gas clouds break apart into clumps that become stars. Preventing that fragmentation requires special conditions, intense radiation, rapid cooling, and extremely low metallicity. This paints a picture of a very narrow window in cosmic time, a moment when the conditions for direct collapse were just right. And it raises the possibility that the ancient black holes we see today are fossil evidence of a fleeting, exotic era in the universe's evolution, one that ended as the first stars polluted space with heavier elements. This notion that certain cosmic processes only happened during a brief primordial phase mirrors other ideas in modern cosmology. For instance, inflation theory proposes a split-second expansion of space-time after the Big Bang, shaping the entire visible universe in less than a blink. Could black hole seeding follow a similar logic? A burst of activity, then silence? Still, some astrophysicists weren't satisfied. They argued that even direct collapse black holes might not grow fast enough without fine-tuned conditions. So attention shifted once again from physical collapse to theoretical frameworks even more speculative, the realm of modified gravity and exotic cosmology. A few bold theorists proposed that perhaps gravity itself behaved differently in the early universe. General relativity, Einstein's crowning achievement, has passed every test in the modern era. But it hasn't been confirmed in the extreme densities and energies that prevailed just after the Big Bang. In modified gravity models, such as F-R gravity, scalar tensor theories, or higher dimensional frameworks, gravitational attraction could be stronger or behave differently at certain energy scales. This could allow matter to collapse into black holes more rapidly, bypassing known limitations. These ideas are difficult to test, but they offer something essential, a way to explain not just one rogue black hole, but a consistent pattern of early formation across cosmic time. They hint that the early universe may have had rules we no longer see, rules that faded, evolved, or became hidden as the cosmos cooled. Another set of radical theories came from string theory and extra-dimensional physics. In these frameworks, gravity might leak into additional dimensions beyond the familiar three of space and one of time. This leakage could alter the strength of gravitational collapse, especially in the high-energy conditions of the young universe. Some physicists even speculated that black holes formed not from matter, but from energy fluctuations in the quantum foam itself. These primordial black holes could be born in the earliest instance of cosmic time, seeded not by stars or gas clouds, but by the fabric of space-time undergoing turbulence. These exotic scenarios carry wild implications. If primordial black holes exist, they could account for dark matter, influence cosmic structure, and even provide clues about the pre-Big Bang universe. And yet, despite years of searching, we have not definitively detected them. We only have hints, shadows, and gravitational whispers. The Webb telescope continued to bring new surprises. One object, SUPERMASSIVE 1019, stunned researchers with its unexpected complexity. It wasn't just a black hole or a galaxy. It was both, wrapped in a spiral structure far more evolved than its 500 million year age would suggest. This object broke the timeline. It didn't fit. Another discovery involved a distant quasar whose spectrum showed signs of extreme winds, black hole-driven outflows capable of reshaping entire galaxies. These ancient giants were not dormant. They were active, loud, and dynamic. They heated their surroundings, blew away star-forming gas, and carved out space itself. This suggested a new hypothesis, that ancient black holes weren't just witnesses to early galaxy formation. They were participants, agents that regulated growth, shaped galaxies, and perhaps even determined the fate of stars around them. And as new data poured in, the same themes kept emerging. The early universe was not a slow, quiet place. It was hot, messy, chaotic, and astonishingly productive. Black holes didn't wait. They formed fast, grew large, and made their presence felt. All of this forced scientists to confront another unsettling idea. What if our understanding of cosmic time is fundamentally flawed? Traditionally, we measure the age of objects by their redshift, a stretching of light caused by the expansion of the universe. But redshift depends on assumptions about how the universe has expanded. If those assumptions are slightly wrong, if the expansion wasn't uniform, or if dark energy behaved differently, then our entire timeline could be skewed. That would mean that the ancient black holes we see may not be as ancient as we think. Or worse, they may be even older. To resolve this, researchers are combining cosmic observations with models from quantum cosmology, string theory, and thermodynamics. They're mapping not just space, but the evolution of entropy and information across the universe's history. It's a new kind of astronomy, not just watching the stars, but decoding the logic behind their very existence. The black holes at the heart of this mystery are no longer just astrophysical objects. They are philosophical puzzles. They ask us to reconsider what it means for something to exist, to begin, to change. And they do so not with quiet, but with power, with light, with gravity so intense it bends not just space, but understanding. In the last few years, some physicists have even begun to call these ancient black holes cosmic fossils. They are not alive in the biological sense, but they are relics, preserved snapshots of a universe we cannot recreate, only observe. They are older than galaxies, older than the stars that shine in our sky. And perhaps, in some strange way, they are older than time itself, if time is merely a story we tell based on change. As the data mounts, a new picture is emerging, one that is more complex, more chaotic, and more beautiful than we imagined. The ancient black hole should not exist, yet it does. And in its persistence, it tells us that our theories are incomplete. Our models are approximations. And our universe, this grand, expanding ocean of matter and mystery, is far more strange than we dared to believe. The final reckoning with the ancient black hole brings us to the edges of cosmology itself. As theories multiply and observations become more refined, one thing becomes clear: this discovery isn't just about a single object. It's a crack in the mirror, one that reflects not only the cosmos, but the assumptions we've held about it for decades. From the outset, black holes have been paradoxical. They are the ultimate collapse of matter, regions where density becomes infinite and the known laws of physics cease to apply. But in their silence, they tell stories of stars, of galaxies, of time itself. And when one appears earlier than it should, it tells a story that shouldn't be possible. The more physicists studied this ancient black hole and others like it, the more they realized how precarious our cosmic understanding truly is. In standard cosmology, the timeline is supposed to be linear, rational, and layered. First the Big Bang, then a cooling universe, then the first stars, then galaxies, and finally, at the hearts of those galaxies, black holes. But these discoveries reverse that logic. They suggest that black holes were not the end of the cosmic timeline, but possibly the beginning. This flips an entire field on its head. What if black holes were not byproducts of galaxies, but catalysts? What if gravity didn't wait for galaxies to form before it started its great work? Instead of emerging last, what if black holes emerged first and everything else followed their lead? This idea isn't just speculative. It has deep roots in general relativity and quantum gravity. If black holes could form from dense energy concentrations without needing matter, then the very first instance after the Big Bang might have spawned a network of them, micro, meso, and megascale. These primordial black holes would then act as gravitational anchors, drawing in gas, sparking stars, and building the large-scale structure we see today. In this vision, the ancient black hole isn't an exception. It's a rule, one we've only just begun to understand. But there's another implication, one that's even more haunting. If ancient black holes shaped the universe, and if their properties were determined by the earliest quantum fluctuations in space-time, then perhaps they carry information about realities beyond our own. According to the holographic principle, a leading theory in quantum gravity, everything inside a black hole is encoded on its surface. This means that each ancient black hole might be a library, holding data about the very first moments of existence, written in a language we don't yet know how to read. And then comes the multiverse. Some versions of string theory propose that black holes might be gateways, not to wormholes as Hollywood suggests, but to entirely new regions of space-time. In this view, every black hole could be a bubble in the cosmic foam, leading to a different universe with its own laws, particles, and dimensions. The ancient black hole, then, might be not just old, but foreign, a relic of a previous universe, or a cosmic scar left by an event beyond our horizon. We don't know, and that's the most honest thing we can say. For all our instruments, all our data, all our theories, this black hole remains a mystery. Not because we haven't tried hard enough, but because the universe is under no obligation to be simple. It's messy, it's strange, it contradicts itself, and that, perhaps, is its most profound truth. As we close this chapter, we look to the future. New observatories like the Vera C, Rubin Telescope, the Nancy Grace Roman Space Telescope, and future gravitational wave detectors will provide even more data. They may find more ancient black holes. They may detect mergers at redshifts so high they bend the very timeline of space-time. They may confirm that these objects are not rare, but common, and that we've only begun to scratch the surface. The next decade of astronomy will be transformative, not just because of what we'll see, but because of how we'll think. The discovery of an ancient black hole that shouldn't exist has already changed the game. It has forced theorists to revisit foundational assumptions. It has sparked new collaborations between particle physicists, astronomers, cosmologists, and data scientists. It has reminded us that the universe is not a solved problem, it's an open book. And the first few pages are missing, but in that gap lies potential. The potential for a new kind of science, a new kind of curiosity, and perhaps a new kind of awe. Let us end where we began, not with answers, but with a question. If one black hole can rewrite cosmic history, what else is waiting to be discovered? Because this universe, our universe, is not finished telling its story. It has only just begun. Now, as you sit back and breathe in the silence of space, picture that ancient black hole again. A pinprick of darkness, older than light, older than galaxies, suspended at the edge of time. It doesn't shout. It doesn't flash. It simply is a quiet witness to creation. Around it, the early universe swirled with chaos, collapsing gas, fierce radiation, stars being born and dying in the blink of a cosmic eye. And through it all, this black hole remained, steady, persistent, eternal. We gaze at it now from across 13 billion years, peering through lenses of glass and mathematics, hoping to decipher its story. But maybe, just maybe, some mysteries aren't meant to be solved. Maybe they exist to remind us how much we don't know, how much wonder still awaits us. So let the darkness comfort you. Let the unanswered questions hum quietly in the back of your mind. And know this, in the grand dance of the cosmos, we are lucky just to be here. To look, to wonder, to ask,